Good morning. Is there any questions? Positive? Um, I thought I put about the final. Let's just be here right now. So project 5, I believe it's due this week. We'll look at that in a second. But your final is Wednesday, May 10th. And notice it's at 8 a.m., not our regularly scheduled time. So you want to be careful of that. Any questions on that? The project is 55 points. The main post is due April 21st, which is Friday. And you need to respond, I believe it said 3 people. Yeah, at least 3 people by Sunday. Any questions? Think about the exam problem with the deer and the carrying capacity for Mill Creek Park that was on the test. And that's kind of the idea. It's up to you if you choose an animal, a plant, or people that are in a certain area. That's up to you. You could do like population of China and compare it to its size and then see how many people should actually be in that area. Or whatever, wherever you live, you could do that. So animal, people, or plants, it's up to you. Any questions? There will be one more project to do. And I will put it up sometime this week. So there's a project, the final, and your attendance problems. Any questions? We were on section 5.3 and we stopped here with the large numbers. A law of large numbers for random variables. Imagine a random process such as a game of chance that can be repeated many times independently. Let x be the random variable associated with it. Then e of x equals m, the expected value. The average value x after sufficiently many trials will approach that. So say we're tossing a coin and maybe the first, you figure if we're going to do it 10 times, which we did do, when we toss a coin, half of them should be heads and half of them should be tails. So if we counted the number of heads, we should have 5 of them. what the law of large numbers tells you is the more you do it, the more you will get closer to half of them being heads. We could toss it 10 times and all 10 of them could be tails. But the more we do it, the closer we'll get to half of them being heads and half of them being tails. And that's what the law of large numbers tells you. The more you do it, the closer you'll get to that probability. So doing it just once or twice, when you're finding these expected values, you may win the first time and then lose everything the second one, but in the long run, it's telling you what you'll average. So let's look at this game. I invite you to play the following game. First, you pay me $1. So all of these to start with, we're at $1 loss. Because you want your value to be the total amount that you're either getting or losing. So we pay $1. Then we flip a fair coin. If the coin comes up heads on the first flip, I pay you 50 cents. So the first time, if you get a heads, you get 50 cents. Which means if you toss heads the first time, you're at a loss of 50 cents. Because we won 50 cents, but we had to pay $1, so we're still out 50 cents. Any questions on that? If we don't flip a heads, which means we got a tail, we flip again. If the coin comes up heads on the second flip, I pay you $1.25. So if we get a tail and then a heads, we're going to get $1.25. But it costs $1 to play. So now we're up 25 cents. So right now, this is the better one. You want to get a tail and then a head. If we don't, if we get 2 tails, we flip a third time. On the last flip, if the coin comes up heads, I pay you $3. So if we get 2 tails and then a head, we're going to get $3, which means we're up $2. If it comes up tails, you get nothing. You lost your $1. So when you're finding the value, if you had to pay to play the game, you have to remember to subtract that out. Any questions on the first part? If we toss one coin, what's the probability of it being a head? Anyone? If we tossing one coin, the number of outcomes are 2, a head and a tail. So there's 1 out of the 2, or 1/2. And you could use the decimal since these are in decimals if you want. Or you could keep the fraction. I think for the last project, I might have you create a game of chance, like tossing a coin, flipping the die, and you pay so much and then so many winnings depending on what it lands on, or you can use a spinner. But I think that would be fun. Any questions on the first probability? The next one, we're tossing 2 coins. If we want to find the number of outcomes, when you toss the first coin, there's 2 heads or tails. When you toss the second one, there's a heads or tails, so there's 4 outcomes. Now we could do it this way, and then find the probability of a tail and then a heads. There's 1 that will have the first one a tail and the second one a head out of the 4. The other thing is, because of they're independent of each other, one does not affect the other. We could take the probability of the tail times the probability of the heads. Each tossed separately. The probability of a tail is 1/2. The probability of a head is 1/2, which gives us 1/4. Both ways for a thought process doesn't matter. And again, if we're going to use the decimal, 1/4 is a quarter. You wouldn't want the percent though, because to multiply across, you'd have to rewrite it. So either the fraction or the decimal. Any questions so far? Okay, go ahead and find the next 2 probabilities. Now remember, we're tossing 3 coins. Find the number of outcomes. Then we need the probability of a tail, and then a head, and the probability of all 3 tails. How many outcomes are there? We're tossing the coin 3 times. They're all coins, so they all have 2 outcomes. So total number of outcomes is 8. Instead of adding the 2's, you should have multiplied. That would be 2 times 2 times 2, which would be 8. So then the probability is 1/8. Right idea though. Because we're talking about that exact order, there's only one way of doing them. So 1/8. But for outcomes, make sure they're multiplied. And then again, this can be the fraction or the percent. Oops. Any questions on that part? So we want to fill in the table and find the expected value. To find the expected value, take each value times its probability. That's what the contribution means. So you take this times this all the way across these 2. And then when you add them up, that's your expected value. And I think, did it say what WB winnings? I don't know if it said it. But the So the expected value for winnings. Multiply across. Any questions on the multiplying across? Now the positives doesn't have to be a plus there. I like to put it because then I remember that I checked my sign. And I know it's positive. Now if we add these up, you should get negative 0.0625. So you're going to lose about 6 cents every time you play. Now, of course, if you only play once, 6 cents isn't a possibility. But in the long run, if you play it many times, you'll average a loss of 6 cents per game. Any questions on that? Can we always do? Yes, unless I specify, there's some cases I want to make sure you know how to write it in different forms, but you can. The only time, be cautious, if this is a decimal that keeps going, for instance, if this is 1/3, you want to keep the whole decimal. So then writing the fraction is probably better because you don't want to round till the end. So you want to keep 1/3, 0.333333, putting 1/3's better. But technically you're fine. Just don't round this to 0.3 or 0.33 because the expected value will be less accurate. But this one rounded nice. I was able to keep the whole decimal, so I used the decimal. But a repeating one, I would probably use the fraction. Any questions on that? Now, the other thing this is saying is if I played this 100 times, how much will I win or lose? Well, we know it's going to be a loss because it's negative. To find out how much of a loss, you take your expected value times the number of times you're going to play. So if I play $100, I will be out $6.25. And I said $100 because it says $1 to play each time. So if you played it $100 times, you're only going to be at a loss of $6.25. So if it's fun to play, you may want to play it. 100 times, you're only losing $6, a little over $6. 1,000 times, you'd be losing $62. So you will win sometimes. And you know, if you're lucky, maybe you get two tails and a head most of the time and keep up with the $2 one. But any questions on that? Now you can look at this also when you're talking about car insurance, a lot of different things. You put weights on them. Now in this one, your car's worth $7,500. You pay $40 per month for 1 year of insurance policy. That's really low. Oh, I guess because of the value of the car. So we pay every month for a year. The insurance policy that will reimburse you the value of the car if it is totaled. To keep things simple, let's assume that for a lesser accident, the policy will pay nothing. So this, even though it's only $40 a month, it will only cover the car if it's totaled. A simple accident, it will not cover. The probability that you will total your car in a given year is 2%. So we don't need the insurance if we don't total a car. We need it. This is the case where you total car. So this is if you don't need need to use it in a year, and this is that you do. If you don't need the insurance, you're paying $40 a month. How much are we out? How can we find this value? So if we're paying $40 per month for 1 year, 12 months in a year, we are paying $480 for this policy. If we don't need it, we're not going to get any money back. We're losing all $480. If the car gets totaled, we've spent $480, but we're getting $7,500 because it got totaled. Which means we're making $7,020. So if we pay for insurance and then don't need it, we lose $480. If we do total the car, then we're going to get $7,020 because we're subtracting what we paid for the insurance. Probabilities. The probability you will total your car in a year is 2%. Total the car, 2%. Written as a decimal. If totaling the car is 2%, what's the probability we don't total the car? Anyone?
98%.
Because remember, the two need to add up to 100. This is the complement. When they're written as a decimal, they need to add up to 1. Any questions on that part? So the . So to get the 0.98, the probability you don't total your car is 1 minus the probability you total the car, which was 0.02. 1 minus 0.02, 0.98. Any questions on that? Okay. Then just multiply across to get your contributions. Our expected value, we add these together. $330. Now, of course, in 1 year, we're either at a loss of the 480 or a win of the 70-20. But over time, we will lose on average $330 a year. Now, of course, there's other things to take into consideration. Each year that the car gets older, its worth goes down. So you may even get less. But for this 1 year, you're at a loss. Any questions on that? Now, of course, what if you do total your car? Maybe you do want to make sure you're paying this because you don't have the money to pay the $7,500 to replace it. Chances are it probably will be even more than that to replace it. So there's other things you're weighing besides just the expected value on certain things. Is there any questions on that?
What is the expected value telling us again?
It tells you in the long run, you will be at a negative 330 a year. So if this value and everything stayed the same, in 10 years, you would have lost $330 per year. So it's telling you in the long run how much you lose, in this case, per year. The other one was per game.
Oh, okay.
So if we looked at, say we did it for 20 years. Then we would take 20 times the expected value. And we'd be out $6,600. Now, if we just look at the cost of the insurance, we have made some money in there. So we've paid $9,600 over 20 years. But it's showing we're at a loss of $6,600. And the reason for that, there's other things at play when it comes to insurance. You could have totaled that car, got another car and keep the same policy and then totaled it again. But this is awesome. So expected value tells you how much you expect to pay over the long run per whatever the time is, per year, per game. Any questions on that? Some more rules. Linearity rules. If we're adding two, say we have two different expected values and we want to add them together, you can find the expected value of each and then add them. If you're multiplying by a constant, like the 20 years, you can find the expected value first and then multiply by that constant. I don't know how much we would use this. Maybe this one kind of here. We could have put the 20 years into the problem or find that and then multiply. Yes. I don't use this one a lot, but it was there. So I thought maybe if one of the problems come up using it, we'll have it. But this one's used more. We had this formula or definition before. Random variables X and Y are independent if knowing the value of X does not give any new information about how likely Y is to occur. And we've talked about that. If you think of a deck of 52 cards, if I'm going to draw two cards, when I draw the first card, if it's, we'll say a king. If I keep that card, then I only have 51 cards and I don't have a king of hearts. So it's changing, it's giving me new information about the next one. If I put that card back, then all the cards are there. I haven't changed anything when I go to draw it the next time. So if probabilities are changing or values are changing, then it is not independent. But if you put the card back in, they are independent events. Any questions on that? So rolling one die and then rolling the die again, those are independent because my probabilities are not going to change. There's still all 6 numbers on the die. Now, if you covered, say you rolled a 3 and then you cover that value up with a piece of tape, and then you have to roll again until you get another number, that's changing the probability. But for the most part, tossing a coin over and over again or rolling a die, those are independent because your probabilities are still all the same. Any questions on that? Now, when you're using this product rule, they do have to be independent of each other. And I did do this with the tossing of the coin. I said you could take 1/2 times 1/2 rather than finding the probabilities together. So if you're finding the or let X and Y be independent random variables, then the probability of X times Y is the same as the probability, or not probability, sorry. E means expected value. But when you're finding the expected value of the two multiplied together, you can find them separately and then multiply. Because sometimes it's easier to do it separately. But they have to be independent. Okay, expected utility as a guide to a decision, because we said like with the insurance, there's a lot more at play, and some of that you can weight with a utility. Our discussion about bets and insurance purchases suggests a way to make decisions in the presence of uncertainty. So we don't know what's going to happen to the car, and we have to take a chance. Although you cannot drive without insurance, so maybe you use less insurance, but driving without insurance is illegal. So you can't really decide no insurance, but you could do less insurance. This is the expected utility rule, not a mathematical rule like the linearity and product rules that we just discussed, but a proposed guideline for decision making. So by looking at the expected value, you can help decide. And it's going to show you another rule on the next page. Expected utility rule. When making a decision between uncertain alternatives, choose the strategy that has the greatest expected payoff. So whichever one has the best payoff. We use the word payoff here in a general sense to cover not only financial payoffs, but any other kind of reward or incentive that can be measured numerically. Economists often speak to such rewards as utilities. In this context, utility does not mean the power company. It is just a fancy word for usefulness. And that is why this decision-making rule is called the expected utility rule. Now with this rule, they're using the symbol, and I think they bring it more in the next section, but I wanted you to know what it means. This line means the conditional probability that A occurs given B has already occurred. So the probability of A given we know B occurred. Now for this first part, we don't really need the definition or the formula, but I thought it was good to give you it. So the probability of A given B is the probability of A and B divided by the probability of B. It may or may not rain today. And I'm wondering whether I should bring my umbrella. Some economists suppose that consciously or unconsciously, my decision process involves quantifying the pleasure and inconvenience involved in various decisions. Carrying my umbrella on a sunny day is inconvenient. And they're going to say they give it certain points depending on what it is. So carrying my umbrella when the sun is shining, it costs me 2 units of utility. So having to lug that extra piece, think of how much annoying it would be to you. They're saying that value is 2 units. The joy on a sunny day without inconvenience is a gain of 3. It's sunny out. You don't have to carry your umbrella. You're feeling good. It's a gain of 3 units. Well, now you need to think about what if it is raining? If I don't have an umbrella and it rains, I get wet. That's a big unfortunate. They're saying a cost of 15. And that's rain. And of course, the last one, if it rains and I have my umbrella, I don't get wet, but I don't enjoy the day. So it's just 0. Now, I like the rain. So maybe the rain and I have my umbrella, I may gain points here. So there's no right or wrong. It's all in how you feel about it. But in this case, it's 0. This information can be codified into a payoff matrix for the random variable U that measures the amount of utility I gain from my trials under different conditions. Now, the umbrella and it rains, we said it was 0. If we have our umbrella and it's shining, carrying my umbrella on a sunny day costs me 2 units. No umbrella and it rains, that was a big one. It cost me 15. So you're putting a value on it. Not necessarily money, but a value. This one, no umbrella and shiny, 3 units. Any questions on that part? Suppose now that I hear from the weather forecast that the probability of rain is 40%. What's the probability it won't rain? Anyone?
60.
Because it's 1 minus the probability of rain. Remember the complement? 1 minus 0.4, 0.6, or 60%. Oh, I wrote it up there. So we need to decide what to do. Well, we could look at these 2 probabilities. Okay, the first one is the probability of the utility given we take our umbrella. So we're using the umbrella row. And I'm going to put the probability here. Probability of rain is 0.4 and shine is 0.6. Because remember, expected value is your outcome times your probability. Or your value times your probability. Now, umbrella, we go across. 0 times 0.4 plus a -2 times 0.6. You could have just put -2. So the expected value or the cost of bringing my umbrella is a -1.2. The cost or expected value if I don't bring my umbrella. no umbrella. -15, 40% chance. A gain of 3, 60% chance. So the expected value, if I don't bring my umbrella, is a -4.2. Where bringing my umbrella is a -1.2. Even though sunshine and no umbrella makes me really happy, this is a lot lower value. So what they're saying is you're better off doing this one and bringing your umbrella. Any questions on that? So you can look at your expected value as, and maybe this would be higher, and maybe this would be higher. I mean, if I'm carrying my umbrella with my book bags and my computer and my Diet Coke, I might be really happy if I don't need my umbrella. So it may even be higher than this. It just depends on each person, how far you have to walk, if you're just parking right outside your building and running in. So these can have different weights for different people. So then the expected value could be different. But according to this one, you're better off bringing your umbrella. You'll be happier. Any questions on that? Positive. I think 310 is just where I left off. But we'll stop there and continue tomorrow. Is there any questions?